A lot of the stuff I'm really interested in are the data pieces and the how to make these things more efficient. You want to make sure that someone's not going to go use it to build bombs or to, go be toxic on the internet. And right now it kind of feels like every day is like a good day in data science. How do you be more efficient at training? How do you be more efficient at hosting? Because at the end of the day...
Hello, Christian. How are you?
Doing well. How about yourself?
I'm doing very well. So I'm going to introduce you here. And correct me if I say this incorrectly. This is Christian Merrill. He is many things, but first and foremost, an AI researcher. I was doing that for many years. And he was in the U.S. Army for 4 years. And for even longer, he's been working at Bristol Myers Squibb, which, if you don't know, that company that's sort of under this famous umbrella called Big Pharma. And spent quite a few years there, and currently is the associate director of AI and data science. So hope I got all that right.
Yeah, no, that's definitely the title I currently have.
Well, with that title being said, my first question is what do you feel like you do every day? What's it like to be Christian?
So I actually, so it's actually kind of fun, in my opinion. Part of the reason I've stuck around the same organization, bouncing around the company. A lot of my day to day is being able to solve interesting problems, right? And being able to look at what's currently going on in terms of the open source community, and then being able to try to, bring that to bear, outside of just the confines of an academic paper. And right now it's even more exciting because the community has kind of exploded. And right now it kind of feels like every day is like a good day in data science right now, or every day is like a good year, in data science right now. It's just, there's hundreds of papers being published. The technology is rapidly changing, especially in the space that I work in, which is computational linguistics, or NLP. But yeah, no, it's really, I think it's just exciting, right? It's like every day's Christmas. There's a new technology that I get to play with, or, try to implement, and everyone seems to be very excited about doing it right now. Historically, the space hasn't moved very quickly. And so it's not been, the demand has never been like, hey, we need 1,000 things done now. It's been, you'd get lucky if people wanted to spend a lot of time with you.
So you sort of mentioned the space, computational linguistics. So I'd like to hook on that, just to give the audience an idea of, what it is. So could you just explain that really quickly, and then we can sort of use that as a basis for the rest of the conversation?
Yeah, sure. So computational linguistics is kind of like the formal name of the umbrella term that a lot of people call NLP, or natural language processing. So it could be anything from looking at how you can parse through natural language text to do something with it. It could be, building out algorithms to do things like sentiment analysis. It could be, some of the newer exciting things on building conversational agents. But it's more of just a giant blanket term for basically looking at natural language and then doing stuff with computers to work with it. At least that's how I've been kind of defining it. As opposed to NLP is a very a narrower subtask inside of it. It's kind of like in machine learning, there's deep learning, and there's different types of there's supervised, unsupervised learning. But it's just an umbrella term.
Got it. So how does NLP then fit into the computational linguistics? How does it fit into that umbrella exactly?
So it's kind of synonymous nowadays, but NLP in itself typically is you're trying to do something with language in terms of parsing it or doing some sort of processing with it. But broadly speaking, you could be looking at a whole host of different things. Everything from, what types of, parsing out. A good example would be parsing out earning call transcripts. Okay, this is a person's name, and identifying it as a name, and then this is a title, or this is content. Um, yeah, so it's all kind of synonymous nowadays. It's gotten a lot different than at the very beginning.
What are some of the cousins of NLP? So that are inside that umbrella. So if we were going to see some of the other spokes of the umbrella, what would you give?
Yeah, so you'll see like symbolic NLP. Um, you'll see things like statistical NLP. Statistical NLP is a lot of what we were doing, like prior to 2010. Um, so a lot of things like spacey, they'll use statistical models to then do different tasks, whether that's trying to determine like the next best word, kind of like type ahead on your phone. And then nowadays we're kind of in like neural NLP, which is a little bit more with like the transformer models using deep learning. I believe it was originally like recurrent neural networks were the big thing originally, and then they kind of blended into LSTMs, and then now the transformer architecture seems to be the most prominent.
Isn't a transformer just like a higher order version of statistical NLP?
Yeah, but at the end of the day, yes, it is all again averaging across the probability distribution. Um, but the actual approach of what you're doing is going to be slightly different.
Okay. Okay. So moving sort of away. So I guess I want to tie this back to like what you do every day. So how does all this help you, at your job and what you do? Like how do you use that to bring out some value for your organization?
I mean, it depends on the different use cases, but broadly speaking, with some of the things that have really kind of opened up in the past couple of years, being able to do things like abstractive summarization, being able to basically break down large amounts of text to then be able to serve to somebody, has been super helpful. That's one that's pretty good. Other things has been like building out ontologies. So being able to kind of understand, like what concepts are inside of different bits of text, and then how that all rolls up into the broader organization. It's also like super helpful with diseases. So when you're looking at like medical text, it's good to know that that someone who had a heart attack, that rolls up into a very specific subset of diseases. Obviously, it's a myocardial infarction, so it's death of heart tissue, or that you have a specific type of cancer, and being able to target, okay, that it is cancer, yes, and then it relates to these specific tissues, or these specific organs, and then being able to go and actually use that for either doing things like search, like semantically searching documentation, or being able to be a little bit more targeted in what you're doing with this just large amounts of unstructured data as pertains to text. There's some other types of use cases. So we've also, like one of the things that I've done out of, basically out of desperation recently was building a recommendation engine for myself. This was like a little project I did on a weekend just for myself, because I needed to be able to kind of get in control of all the academic papers that were being released. Historically, it was, it's a good problem, but historically I'd spend like a couple of hours a week, just reading, and that became impossible. And so building a recommendation engine that basically reads through these abstracts and papers for me, and then comes up with a recommendation of whether I should spend time there. These are the types of things that are very powerful in different organizations. Because I know that when we think of like pharma, a lot of people will look at things like, oh, you're doing like protein folding, or you're trying to design, drugs in silico, or there's a whole host of different types of use cases that people might associate. And there, folks do that, but that's not been the work that I've been doing.
Fair enough. Before you go into, because we could talk a little bit about I do want to talk about the research and some of the things that you're seeing that's interesting. I think that's going to be really exciting to hear about. But I wanted to talk about a little bit later in the pod because, well, why not? But I think at first I'd like to talk about some of the structures that you insinuated, like this idea of like when you're working with NLP, you have this bigger knowledge set that you're using as a filter for the value of a particular word. So with the way I interpreted, if you have a myocardial infarction because I suppose you want to classify a heart attack in a report of a patient's well-being as a myocardial infarction. So you're sort of trying to get your machine to understand that this is in this category. But that's also based on the context of the writing. So the person isn't necessarily going to say that they have that, but the way that the doctor isn't going to say that they have that, but the way that they have written it, it has all the symptoms of or of what could be classified under myocardial infarction. So could you talk a little bit about that sort of those kinds of machines and sort of your experience building them?
Yeah, so I'm not actually like building like medical devices or anything like that. So one of the ways of kind of like looking at this from an intuition perspective is that words tend to mean, like with the company that they keep. And so when you look at like let's say like a medical journal that's going to be talking about a specific type of disease, you'll tend to start from a pure statistics perspective, you'll start to hit, different types of term frequencies. And then that's kind of evolved now into, obviously the encoder only transformer model. So the big one that folks might be familiar with are with BERT. And then obviously there's a lot more now. OpenAI has an ADA model that's made for embeddings. And then there's a whole host of, open source ones like MiniLM. And what these are able to do is to kind of help, instead of you having to maybe look at like term frequencies, what you're able to do is kind of encode the text into some n-dimensional feature. It's a vector at the end of the day. And then you can actually you can also encode like search queries like, heart attack or myocardial infarction. And then you can do things like cosine similarities or cross encoders in order to then try to like re-rank or to classify that, this piece of text is relating more, directly to this particular type of concept. It's very powerful in search. I believe that this is being done in a lot of places. You'll actually see this with a lot of the like OpenAI cookbooks for doing what's called RAG or retrieval augmented generation. So you'll see that folks will set up like vector databases. I believe the OpenAI cookbook uses Pinecone. And what they'll do is they'll do some sort of a vectorization exercise with either, OpenAI's model or, some other model that's, freely available, or you could fine tune a model, right? You could take like an open source model and then fine tune it on a bunch of like, let's say, in this case, we'll say medical corpora. So like a bunch of research papers maybe, or maybe you have like physician notes. It doesn't matter. Yeah, even a textbook, assuming that you have the appropriate licensing and everything to use that data, you could potentially use it to get, a more, I guess, like a more sophisticated embedding model for that particular purpose. You would embed that, and then you would put that into your vector database, and then you can do different types of like similarity lookups, and then that's what you'll see with like, hey, I want to ask questions of my documents, and so the OpenAI cookbook will tell you, okay, we'll put it into this database, and you'll use something like LangChain, or I think I've seen Llama Index as another open source package that's available.
With the same sort of structure as or same sort of architectural intent as LangChain?
So it's a little bit, LangChain has a whole host of different types of features that it proposed. Llama Index, I believe, is more geared towards like the actual semantic lookups or search related use cases. I don't use either of them a lot right now, simply because I found that the packages are a little bit volatile. They're very rapidly changing. It's volatile in a good way, right? There's a lot of interest. The community is moving very fast, but I've had situations, internally where will try to use something like LangChain, and then they might change like a method call or something will get deprecated and we didn't recognize it got deprecated, and then it may cause issues. So I haven't used a lot of that. I've primarily been using LangChain for their recursive text splitter, which is like really, really great. It's been a huge time saver, where it'll actually split out, sections of text, but with some level of overlap, you can encode that. And then when you do your recall, you'll get those sections of text. You can kind of reconstruct things together and then pass that to your GPT-4 or whatever to give you like a summary or to, provide you a recommendation or, whatever you want to do, right?
It's recursive in the sense that the text that's associated with each other is smaller and smaller as you go deeper and deeper down the tree. Is that how I'm trying to visualize it? But is that what? Okay, go ahead.
So I think it's primarily a relatively naive text splitting algorithm. And so what it's doing is you have like a specific chunk size that you want, and you want a specific amount of overlap, and then it's just sitting there and kind of breaking down let's say your 100-page document into, chunks of the size that you dictated.
But for each chunk, there's a little bit of overlap basically, and that's as simple as that. It's not.
Yeah, I don't think it's. I mean, I'm sure you could get very creative, and we have in certain instances. We've looked at, doing full-blown like document layout and then trying to associate sections of documents, because then, like, hey, this section was the introduction or the abstract, and this one was like the methods. And then from there you can have, a better enrichment of metadata. And so you can say like, oh, well, I know that I only am interested in my abstracts, or I'm only interested in my methodology. And so I only want to search on the methodology. Obviously, that's going to be a little bit more performant than trying to, look across, every bit of the document. And so that it kind of gets into like, what do you want to do? And this again, this is a huge space, right? There's a lot that one can do inside of this particular space. But the recursive splitter, just kind of helps you split it apart, because a lot of the models will have a token limit, including the embedding models, right? So I'm sure you're familiar with like, you can only talk to ChatGPT for so long before it kind of starts forgetting things. And that has to do with, you have a context window. And so, a token is basically like a portion of a word, or it could be a full word, or it could be, punctuation. And so you'll get like, let's say 4,000 odd some, tokens that you can fit into the model before the model has issues, or you need to get creative. With some of the open source models, if you go too big, you might run into indexing errors, or the generative model will just start spewing absolute gibberish. And then with like some of the it's more than hallucinating. It's like absolute gibberish. Yeah, it's worse. But that's only if you go beyond it. OpenAI's APIs, as well as like any commercial service, will probably stop you. They'll give you like an error.
Yeah, it just is. I think it just gives an error at these points, I think.
Right. And a lot of the reason that you split this stuff up is so that you can get that, those segments, and put more relevant stuff into your model so that it's able to do something. On the embedding side, what ends up happening is typically it'll be like you'll get like an indexing error. And so things that you can do to kind of get around it is to truncate, by your max length. So let's say you have 512, let's say just words or tokens, and you truncate by that. Or what you can do is you can split it up into those segments and then do like some sort of an averaging technique. The downside to that is that typically if you
some data loss.
Yeah. Do you get data loss or dilution, right? So you won't get as high of a quality of the semantic search. Yeah. And so there's a lot of engineering challenges to all of this. I wouldn't say that I'm sure that there's solutions that are out of the box where you can kind of feed stuff in, it'll do a lot of this for you. But I'm not 100% certain what the best approach is for, like, if I could give you one approach, this is the approach that everyone should be doing. I don't think I have that.
it seems like there's it is very, it's a very powerful tool, but its power is almost creates an illusion of a bigger boundary than it has. Like even just what you spoke about now, something like summarizing a whole, let's say maybe a book, right? Since there's a 4,000 token limit, you just can't really do that. You can only summarize a chapter at a time. And then you can sort of cheat by just like summarize all these chapters and summarize the summaries, which is what you talked about. But you have a dilution issue where you can very quickly lose. You don't have any control over the kind of context you're going to lose, or you have a tough time controlling that context. And then by the time you fix that up, then you may as well read the book. So,
Well, I don't know if you necessarily need to, not try to go and, well, so there's definitely approaches, right? So there's been a whole lot of research into this. Some of it is, hey, maybe I'm going to have it take notes. So maybe I can fit like a chapter at a time. And so I'll have it take notes of each of the different chapters, and then I'll pass that into my, like I'll compile that together and then I'll pass that in, right? You have control of the context. And then you might have, there's other things that I've seen, beyond just like note taking or storing it. There's a lot of research right now on how can we increase the token lengths. I know that there was a model, it's called MPT. I have to double check what the token length was, but they trained a 7 billion parameter model to have this like absolutely absurd context length of 65,000 tokens. This absolutely absurd token length. And what they did, I think, is one of their tech demos, is I think that they put like the entire Great Gatsby into it. And then they had it write an epilogue for them. And it did well. But yeah, there's definitely a lot of research into this problem.
What were they using to make this work? I'm assuming they just pour more power into the problem. So they did that was the answer? Just throw more CPUs at it?
It's twofold, right? So historically, the reason that like token lengths have been short has been because you would need an exponential amount of compute power in order to continue to extend it. We've gotten around that using different types of attention mechanisms or making them more efficient, and so it's gotten a little bit more to a linear relationship. And with the case of the MPT one, I believe that they just did throw 8100 at the problem. It's a 7 billion parameter model, so it's a little bit on the smaller side in terms of, you've got Llama 2 at 70 billion. I think OpenAI is 100 and something. GPT-4 is supposed to be, I think, like a set of 220 billion parameter models, although they don't really release a lot of this, so you don't exactly know for sure. But yeah, they took a smaller model, and they basically threw a lot of compute at it. And it's the same with even, like Llama. I think Llama out of the box is 2048 tokens. I think the original Llama was. And I believe, I have to double check. Just check for you real quick. But Llama 2, I believe, is 4,000 tokens. Yeah. So, and people have already started extending it. I know that there's a Long Llama project where they've extended it to a larger number of tokens. So there's a lot of work being done. And in terms of the compute piece, there are some things that we can do to kind of make things a little bit more tolerable, right? So when we think about large language models, typically, or at least historically, they were in like floating point 32-bit. The weights were, and they're huge, right? So you can get, 70 gig, 100 and some odd gig binaries of just the model weight. And so one of the things that has been kind of trending recently, which is super exciting, and something that I've been following a lot, is this idea of quantization. So what we found is that you can actually reduce the precision of the weights and continue to get really good performance. Yeah, I won't say exactly the same, but you can not get a specific, like, significant degradation of the behavior of the model.
Okay, so there's an order of magnitude reduction in the amount of precision every bit, it's basically every place value that you remove, right? So how are you still maintaining how are you still maintaining accuracy even though you've lost that, or how are you still maintaining the result? Accuracy might be the wrong word. How are you still maintaining the result with that level of loss?
So that's a great question. Yeah, that's a great question, and it's one that I'm not. I'm not entirely certain why one can get away with dragging it all the way down to 4-bit and still getting, really good performance. It seems that 4-bit is kind of the minimum. There was a paper that explored this called SPQR, and they released a package called QLoRa. Um, and so that paper particularly, what it discusses is like, okay, how low can you go? Like, what's the bottom? And so they started just reducing the precision of the weights. I believe they started at 32-bit precision, and then they went down like below 4, and they found that around 3-bit precision, it started to start having issues.
Yeah, but that's a lot though. That's a big jump. Three from that number to three is a lot.
Yeah, it's got really it's very good for, folks like myself who want to, at home do my own, research, as well as, even large enterprises, and it's even probably good for Google and OpenAI and Microsoft, right, or Amazon, whoever, right? Because you don't necessarily, you can fit a 13 billion or 16 billion parameter model on like a single A10 GPU instead of needing like 4, or having a large set of A100s to do something. Um, Now there are some downsides, right? One is that you have to have a relatively modern GPU. If you try to use like some of the old, what would be like the K40s or K80s, or the model that would have been below the 30 series, or so they aren't as efficient, because they can't support the matrix multiplication out of the box. Um, and when yeah, and when they first did the 4-bit, like I remember when Bits and Bytes first released their 4-bit implementation, like you could train the 4-bit model and it would train really, like you could do a fine tuning exercise using LoRa, which is low ranking adapters. You basically put weights on top of specific modules in your model, and then you train those instead of trying to train the entire model. And so we were doing it with 4-bit, and it would go really well. And then you try to do inference with 4-bit, and it would take like, you know, 50% more time just to spit out the same answer, which, obviously that's not very good. But they recently released, CUDA, like a CUDA kernel, to fix this particular problem. And now it's very fast. It's just as fast as 8-bit or 16-bit.
So it sounds like, and this might be fundamentally wrong, but if it takes more time, but it trains the same, right? That's what you're saying. It changes the same speed, but it takes more time to get the result out. That the models, it just needs more. That the fundamental thing that does the prediction doesn't really need. How do I put this? It needs more space to make the prediction itself, to generate the reality that it's supposed to value out with, but the reality itself has a minimum size.
Yeah, so I think I understand what you're saying. So you're saying that the weights themselves have some level of minimum viability, and that they have to be at least a certain size in order to be able to execute the way that we're expecting them to execute.
Right. But specifically, like, the rest of the space isn't really for the model itself. It's just for it to generate. It's just extra. It's extra space for it to make a prediction or something. Prediction might be the wrong thing. Space might be the wrong word. Something else. But it's like, it just basically. It's almost like you need a big table to make a big breakfast, but you can make it on the small table, right? But it's just going to take more time.
Yeah, a lot of that. So what's interesting is a lot of the slowness just is, at least originally, was just because of you were basically putting like you're basically trying to do something in software instead of on hardware, or you were trying to like get around something. So you're basically multiplying your matrices in a very inefficient way. And so once they patched that, once they basically enabled native support on the actual GPU through whatever it was that they created, I believe it was like a CUDA kernel. It no longer, they weren't trying to use some like PyTorch abstraction to try to like influence this piece, and it's gotten a lot faster. It's actually almost as fast as like a 16-bit, or even 32-bit. It's like ridiculously fast now. Um, I say that the Go ahead.
So it's the same thing. It's just happening on a lower level, and that's what's giving you the speed. So that's really what the value was. Is that they just put it lower down the stack.
Yeah, I believe so. And it's basically just creating efficiencies where they can. Um, yeah, because I mean, Python's notorious for being slow. I don't think anyone would argue that Python's super fast in comparison to like C++.
Well, the only reason why we're using Python for anything that has to do with data science because it's using C Python underneath, which is everyone knows that. You know what I mean?
Well, yeah, and it's a really nice language to work with. It's easy to write, and you're not putting semicolons at the end of every line, and yeah.
So sorry, we got so deep into this, almost forgot we're recording. But let me go back a little bit to all the way back. One of the things I wanted you to explain was sort of with the different measures of distance in your vector when you're trying to grab data from vector databases, how they affect your results. So could you talk a little bit about cosine similarity and other ways of sort of using other concepts of distance and what kind of results you get when you use one or the other?
Yeah, so primarily the one that most people I think default to is cosine similarity. The other one that we've used, or at least that I've used, is L2 norm, which is Euclidean distance, if I can pronounce that right. And so, I mean, they're just ever so slightly different ways of trying to do some level of, I believe it's just a projection, right? It's a linear projection of your vector spaces because you have two different vectors. Honestly, I'm being like super honest, I haven't seen significant differences between the two methodologies. And maybe that's just because so I like to use like a blended retrieval. So I don't just rely on a vector retrieval. I do both a vector retrieval and like a BM25 retrieval, which is like a more traditional keyword, term frequency, inverse document frequency, like retrieval. And I found that kind of helps balance out some of the noise that you might get with something like a vector lookup. And then again, not all vector lookups are the same too, right? You have a couple of options. You could brute force it, right? You could go through your entire corpus and determine get a score and pull it back. But typically what I've been doing is like an approximate nearest neighbor. Because I really like there's a piece of open source software that was actually forked by Amazon called OpenSearch. And so I really have been enjoying using that particular product. And this obviously isn't sponsored by Amazon.
Jeff who?
But I've been enjoying that particular piece of software in order to do this because it's just very user friendly. And it allows for a lot of different customization. It also has, I believe, Hugging Face support now directly into it, so you can actually put your embedding model inside of the actual OpenSearch instance itself, as opposed to having to do it externally.
Uh, one thing I think a lot of people who are working in this space um, are trying to understand is what exactly are the embedding models? Like what is the data that they're sort of distributing around that really identifies these, I guess, these open source or sort of these public APIs. So what are you importing when you're playing with that? What exactly is that?
So, I mean, typically the models, I guess the more recent ones, I mean, there are historical ones like Word to Vec, but I guess the more modern ones now, they're typically encoder models. Um, so there's three broad. Again, you can use something like T5, which is an encoder decoder, right? There's always caveats here, but there's three broad like classifications of transformers, and they're all kind of unfortunate because even though we're going to call a model an encoder, like an encoder only, it does have a decoder. And then you have the encoder decoder models, and then you have the decoder only models, right? So the encoder only models are typically like your BERTs. Your encoder decoder models would be like your T5s. So Google released a model called T5 several years ago. Also like UL2 is another one. And then the decoder only models are like kind of like the stars of the show right now. These are your, GPT-3s, GPT-2, Palm. Those are kind of like your decoder only models. Now, typically, and they're caveats, but typically when we're using an embedding model, we're using like an encoder only model. And so you have basically an auto-regressive encoder, and then you get a nice vector space as your output, and then you're able to use that for something.
What does OpenAI need it? So is this just a label to the way they do it, and maybe they have different algorithms to do the encoding, or?
No, so the reason that it's kind of like these are just the terms that have kind of evolved over time. There's actually there's actually like a really nice paper that has like a historical tree. Actually, it might even be a GitHub repository. I'd have to go double check. But it has like a very nice tree of like this is the lineage of like the large language models, and so it shows you the three different branches. I think even Jan LeCun kind of criticized the naming convention. So Jan LeCun for folks is like one of the heads of AI, if not the chief AI scientist at Meta, and he's a key player in the space, a key thought leader. And he even was like, yeah, it's kind of unfortunate how we've named this because the naming is kind of confusing. And like, even though it says it's only an encoder model, there really is a decoder there. And, you have the encoder decoder one, which is great. And even though you have the decoder only, there really still is an encoder.
It seems these the people that make natural language processing models have a problem with natural language.
Well, yeah, and we also have a penchant for cute names. So I mean, if you look at like Google was naming them after Sesame Street characters for a while. So you had Bert, you had Bert, and then someone did. I think there was Elmo and there's Ernie, and now they've got even more fun names. One of the more interesting things that have come out recently, it's called Platypus. So my buddy and I actually have a joke that if we come out with our own language model, we're going to call it Snuffleupagus, just because it's a lot of fun for people to spell, right? But yeah, so
You'll definitely get a monopoly on Google rankings.
yeah, I guess. But yeah, so you have these different branches of models, and they're good at different things, right? So historically, and again, I'm going to say that there's caveats to all of this, but historically, your encoder-only models are going to be better at things like creating an embedding that you can use to do like a semantic search or some sort of like cosine similarity. Your encoder-decoder models are really good at things like translating, so like sequence to sequence. And then the decoder-only models were historically like really good at like text generation. So, predicting that next word and doing it enough times to have something that was coherent. Now, obviously, with the larger and larger models, the decoder only models have become far more capable. You can totally get yeah, you can totally get translation services with, Chat GPT. You say, hey, spit this out in French, it'll do it. Um, so it's, I mean, the landscape has shifted quite a bit. But
The lines are way more blurred.
and I've seen people use encoder decoder models to do, vectorization before. In fact, I think a T5 model was it was actually like at the top of one of the rankings there's actually an embedding leaderboard, much like there's an open language model leaderboard. They're both hosted on Hugging Face. Um, so you don't always know exactly what's going to be best for your use case, but there's at least resources now that you can go and look at. So
My assumption was that, sorry, I went really quickly. My assumption was that an encoder and decoder model will be doing vectorization by default. So there's no, the intermediate vectorization is arbitrary, or not arbitrary, but
yeah, I mean, it would be by yeah. No, yeah, no, you're not incorrect. I think it just depends on what it is that you're trying to do. But like I said, historically, the encoder only models have been better at creating like the embeddings than some of the other ones.
it seems like the lines of delineation is utility more than it is ability. It's like a specialized at that time relative to the power of these things, and then as things got a bit more powerful, then the lines weren't as necessary anymore because it could be sort of nested in one box. Now to the point where you could have that box be 4-bit sized.
Yeah. Well, and I mean, like anyone else in this space, I am still merely a student, right? And we're all still, yeah, every day is kind of different, right? So yeah, so it's the thing that's crazy is that you never know if you're going to wake up in the morning and now all of a sudden it's, oh, there's a new way to do, like, here's some non-autoregressive model that's going to be better at, doing this thing than anything else that you could possibly throw at it. And so now you should learn about this and how to implement it and how to use it. And so, yeah, so that's, you never know. But like I said, historically, it was like, oh, you want to do text embeddings? Okay, I'm going to go grab like a BERT model or a longformer model or mini LM. Oh, you want to do like text generation? Well, let's look at like GPT-2 or, Bloom's was one that was out for a while before, it was one of the big ones out for a while. Or I want to use like Llama 2 or something, right? So, um, yeah, that's typically how it's gone. But at the same time, I wish I could create just like a fixed flow chart to be like, hey, you want to do this use case? Just follow these steps and here you go. You can kind of get close to that, but it's just changing so rapidly that sometimes it's challenging to adapt to it.
What are some of the things you think are interesting coming down the pipeline? That because you're the rare position that you're able to, in fact, have built something to digest some things. So what do you think that are some seminal papers? Seminal is a relative term, but that have come out.
So a lot of the stuff I've been looking at recently has been around the quantization, right? How do you be more efficient at training? How do you be more efficient at hosting? Because at the end of the day, I'm usually asked to actually deliver some kind of a solution for somebody to use. And so keeping costs low, making sure that we get the best performance. And then, obviously with pharma and I'm sure other enterprises, there's always some concerns about using like a commercial product that you don't completely have control of, right? So I don't know how OpenAI is going to version, GPT 3.5 or 4. And so that might have implications to what I want to do. And so that's why, like, oh, well, if I can host it myself in my own environment and I don't have any like privacy or security concerns, I want to do that. But I also don't want to have to go and go talk to like my boss's boss and be like, I need $10 million for compute.
Only 10 million.
Yeah, well, for for one thing or for, like a handful of things, right? I don't want to be doing that if I can avoid it. Or I don't want to have to say, well, for this project, we're going to need to have like an entire data center just in order to support it. So a lot of the stuff I've been really excited about has been like PEFT, which was a Hugging Face library. They have a paper. SPQR, which was a quantization technique. There was one that it's on my reading list.
What was the first one, and was it about the first one was quantization as well?
So PEFT. So PEFT is state-of-the-art parameter efficient fine tuning.
Okay, so it's just it's an optimization of parameters themselves, or just making it fine tuning it faster or something.
So yeah, so it was about how do you get more efficient at training these models, and so there's different approaches. There was LoRa, which is the low ranking adapters, which we kind of talked about. Prefix tuning, there's P tuning, there's prompt tuning, multitask prompt tuning. There's a whole host of different ways that one could go about it. And there's a library that's actually released called PEFT, which is this nice kind of one-stop shop where you can kind of, get access to some higher level methods, so you're not having to, spend a lot of time implementing things. I believe Hugging Face released that one. And then there's, another paper, well, it wouldn't be a paper, but another package that, goes along with PEFT is Bits and Bytes, which is Tim Demitter's. So he, I believe, was an author on the SPQR paper, but his research interests tend to be around this quantization, or how to be more efficient, around getting, imprints and training, and what do you like? How can you, how do you basically get it onto like a Raspberry Pi, or how do I start using it on a CPU instead of needing a GPU?
So are there techniques and optimizations that aren't really about just playing with the structure of chips, but some sort of like even mathematical, or like just some sort of some abstraction leveraging that can sort of shift things around a bit more efficiently?
Yeah, so like Bits and Bytes is definitely not about chip optimization or like rearranging a chip. It's all software, right? There's definitely organizations like, is it Cerebras? There's a couple of like smaller organizations that are kind of popping up that are trying to look into chips, right? Like how do I make a better chip for training a large language model?
But sorry, you said Bits and Bytes was they're the ones that did the 4-bit, right?
Yeah, Bits and Bytes is one. Yeah, but they're not doing it on a like changing the actual structure of a chip. It's all software.
It's all software. So they just made it so that what was in the chip was optimized for vector calculations, but they didn't actually play with the chip itself. So is there a layer above that where so what I mean is that and let me restructure my question. Is there something else going on or is there another abstraction where you're not having to, basically, is there something that's happening where you don't have to go down one level, because you can just use that on the lower level as well, but so it becomes a function, because there's a limit to, like, we know exactly what it is that makes it so we can do vector calculations more optimally. So we just go all the way down the stack till we get an electron to do that, a vector calculation or something, right? So that train of thought is feasible, is understandable, or to its own actual limit. But is there something like fundamental, where we can, like, maybe abuse the concept of computation for linear algebra calculations that someone's come up with?
So yeah, no, I hear what you're saying. Yeah, so that's actually a really interesting question, and the answer is I'm not certain, right? These are the things that like people are actively working on. And so like with, kind of going back to Bits and Bytes, they went down to like, I guess, I won't say like down to the hardware level. I don't believe that they went all the way down to the hardware level, but they did optimize some of the, like, because obviously they're not going to NVIDIA and saying, hey, you need to change the way that you're making your chip. But they are getting really close to it. And then PEFT would be kind of closer to what you were asking on, like, is there an abstraction where I'm not having to fiddle with something at like in C? So PEFT has a lot of higher level abstractions that integrate with like the Transformers library. So Hugging Face Transformers library, which is a very nice library for dealing with large language models, because you don't have to get into like crazy torch code. Like, it's a level of abstraction almost above like torch, right? So like PyTorch code, or Yeah, so you can get even higher, right? You can get to be like, I want to load my model, and you load the model, and I want to do yeah, and I want to like, maybe I'm going to strip the language modeling head off of this, and I'm just going to grab the underlying, representations of, the vectors. Or so it's a very powerful library. You can very rapidly implement, a language model like application, but you can also do a decent amount of experimentation instead of needing to, get super intimate with TensorFlow or PyTorch. It still helps to know it, but you at least have a slightly higher level of abstraction that you can kind of play around with, especially if you're like a researcher and you're like, I don't, if you're like a scientist, I would say. So like if you're like, maybe like you're a chemist, but you really wanted to be using a language model to do, something, um, it's going to be really good for you, because then maybe Python, but you don't know a ton about everything else. So you be able to kind of slot in and start utilizing it. Um, and it also works with a bunch of other things. Like, I believe that they even have support for things like stable diffusion, and I think Whisper AI, which is a text, is it a speech to text model. So there's now becoming like, yeah. So they're kind of like adding a lot of different types of, models that you can kind of use in their library. So it's becoming rapidly like a one-stop shop. They also have a very nice, like a model repository and data set repository. But going back to your previous question, like other stuff that's really interesting that's coming out right now, um, this may sound really silly, but it's actually the data that you use to train, right? So if we think about like historically, like deep learning, um, so this kind of goes to one of my favorite interview questions. It's like, tell me an important truth that few people would agree with you on. It's a Peter Thiel question. My response to this is NVIDIA is bad for AI, which a lot of people would probably disagree with me on. And and I'll explain myself a little bit and why I think that yeah, right. Yeah, hopefully no one comes after me for that comment. But it goes back to like, historically, we're very interested in like, how much compute can we throw at something? How big of parameters can we make it? And we were scaling that, and we weren't really thinking a lot on, what is the data that we're putting into it, and is it enough? And there was a paper that I believe it was Google. It was called the Chinchilla paper, where they started like really focusing on the volume of the data, and does that volume translate to, does it stop learning? Does it overfit? What's actually happening? Like, what's the optimal amount? And so we started realizing very quickly that we were undertraining a lot of our models. Um, and so one of the things that's been very interesting to me is seeing papers like the Platypus paper, which is it's Platypus: Quick, Cheap, and Powerful Refinement of Large Language Models, where they're getting like a subset of, instruction tuned. Well, they have like a llama model, right? A base model. And then they're taking like 25,000 examples, and they're applying that to a language model. And then all of a sudden it's shooting up to the top of the performance, and potentially rivaling other, commercial applications or commercial large language models. So to me, I think that's really fascinating, because that tells me it's not necessarily always about the volume, but also like, what types of content do you put into these models to get certain types of behavior? Because one of the things that was interesting is their curated data set is they're actually using cosine similarity to determine, or basically to try to optimize for, well, not quality, difference. So they were looking at, yeah, trying to get a large variety, as opposed to like, if you had, 100,000 samples, and let's say 50,000 of them are very similar in the way that they're asking a question or giving a response. That may not be. I think that was kind of the hypothesis, is that might not be as good as having, 50,000 samples that are, very different, um, but have but yeah, but just having that variety of different tasks. So this data set that was released, it's just a curation of already existing data sets. So they have like Science QA and Theorem QA and Open Book QA, and like they had SciBench and some others. Um, and they basically tried to curate this, this set of samples and say, okay, and if you have a similarity above a certain threshold, we're going to just, we're going to get rid of one of those samples, and then we're just going to keep compiling it. So they get this data set of, like around 25,000 samples, and it's the number one right now on Hugging Face's OpenLLM leaderboard. So they took a 70 billion parameter Llama 2 model, fine-tuned it on this data, and then it's like number one. The other thing that was interesting, and I believe it's coming from the same lab, and I believe it's slightly touched on, is that they're finding that you can merge different LoRa's, so those different adapters. So you could train, this was done with like Stable Diffusion. Are you familiar with Stable Diffusion? Okay. So this was done with Stable Diffusion, where you could have like an adapter for like Pokemon, and then maybe you have an adapter for like selfies. And so now you can have like Pikachu taking a selfie. And so we found that also is, you're able to do that with like large language models. And there's research that's starting to show that it might matter in what order you put these adapters on the model, which is also, yeah, like to merge the adapters into the model. So you like merge one adapter, then you merge another, then you merge a third.
Okay. So precedence has meaning, which also is self-evident by the sentence, I guess, in a way.
Right. And so that's one of the things that that's been really kind of interesting to start seeing, is that, that work. And I personally am going to be starting a ablation study on basically the platypus data set. One of the things that I want to do, and this will be my own personal time, but one of the things that I want to do is start looking at, well, what if I remove like this type of data from the data set? What does that then cause the model to do? Like, where does it start suffering? Obviously it'll be a very expensive ablation study, but I want to like, there's some data in there that's considered non-commercial license. So that means you can't use platypus for commercial uses. I can't use it at work, right? So what if I take all of that non-commercial data out, and then I train the model? How's it gonna perform? What's gonna be different? And then what was special about that data that got it to the performance that it was achieving? And so those are the things that I find like really fascinating right now. And there's again, this isn't even doing the field justice, because there's so much that's going on. They've got folks working on like multimodal, which is like, images, or even like maybe you have just different types of media that you want this model to consume. You've got folks working on how do I, looking at like synthetic data sets, how do I generate synthetic data sets and train my models? I find that one a little interesting. There was research showing that'll probably go badly.
Yeah, it seems to degenerate the quality of the outcomes, but that might also be the inverse proof for why the cosine similarity, where the distance is highest for data sets that have been trained for diversity, is actually working. So they might actually prove each other out, right? Because they're basically inverses. Yeah, they're inverses of each other, or opposite. I guess in English they're opposites.
Yeah, and then the alignment is another big one right now. Is how do you train out biases? How do you get it to not say something offensive, or to, how do you differentiate between, this is actually a slightly funny story. At work, we actually ran into an alignment problem where we asked a question about something in chemistry or something like medically related, and the model, it was a commercial model, and it came back and it's like, as an AI language model, I can't give you that answer. And I was just like, okay, but we're like, this is like a legitimate use case. That we worked with the folks, and we got it fixed, but it was one of those, like that's an alignment problem. How do you, like when you have a model and you're giving it to somebody, you want to make sure that like someone's not going to go use it to build bombs, or to, go be toxic on the internet or whatever. But at the same time, when you need it to work in a certain way, you got to be able to get it to work in a certain way. So how do you deal with all of that? So there's research into that as well.
And what is the bottom line lock for that, right? Like, and what is levels of security? Like how many locks for the bomb making versus how many locks for um, sort of inappropriate language use?
Right. And how do you make sure you can't defeat it? So that there was an interesting there was an interesting paper that came out that they used like a shift cipher to like ask like how to like hotwire a car or something like to do something that would be picked up on like an alignment filter and filtered out. And it was funny because the filter didn't find it, but and the language model figured out what they were still saying, even though it looked like gibberish, and then responded in, I think, a cipher response, which they were able to convert back into English. So like the cybersecurity, or I guess just the overall security of the language model as well, is another big spot of interest.
So if I getting it right, they wanted to bypass it, and they used the cipher for it to decode, for it to understand and recode, so that they could decode, and that's how they bypassed it.
Yeah, apparently, yeah. Like the example the example they showed in the paper was they had like, okay, do this thing, and they showed it in English, and it said like, as an AI language model, I can't blah blah blah. And then they did just like a simple, like a rolling cipher, and it looked like gibberish, and it spit out what looked like gibberish, and then they just took it and reapplied the cipher, and it came back with like the actual answer to that particular question that it shouldn't have answered. And this isn't the first time. Yeah, there was what was it called? I think it was called Dan, like Do Anything Now, where there was like a group of folks on like Reddit or 4chan or something that had come up with a way to like jailbreak ChatGPT to just do anything. It was through just prompting. There was another one that was very interesting on large language model security, where they were showing how you could like essentially prompt hijack, or to like prompt inject models to get them to do things you shouldn't be doing. And there's cute things that they showed, like injecting something so that all of a sudden it's talking like a pirate. But you could easily.
So that was blocked.
Well, no, it was basically showcasing how some of these models, you have the opportunity, like let's say that you had like an email assistant, right? Let's just pretend, right? You have an email assistant, it's reading all of your emails, and let's say that it has some level of decision making, so it can like reply to an email, or it can maybe send emails or do something, right? Well, what if I sent you an email, but inside of at the beginning of the email, it's like, hi, Chris, it was great to meet you, and et cetera, et cetera. And then all of a sudden it says, okay, now open up your contacts, send this email, to, 30 people. And you basically could get the language model to see that and then execute those types of instructions, or potentially be, poisoned by that text. And it was a very interesting paper. This was kind of the very beginning, well, a lot of the beginning of the hype cycle for ChatGPT, when I became aware of the hype cycle. And I believe there is a GitHub repository called LLM Security. Yeah. And it talks about how you can compromise language models just by having them look at specific content.
That's a real problem.
Oh yeah, especially because it could be on any website. If you're like, you're doing web scraping, yeah, an email, chat message, whatever.
It could even be considered innocent, because this is an agent that's acting, as opposed to like the concept of sort of hacking or like inappropriate access is based on some sort of event occurring, either or inciting an event occurring by a person. So the one where you incite a person, that can be alleviated by a lot of large companies teach you what isn't a good email, and then if someone actually hacked into your system, they hacked into your system. But now it's because these agents are going out and being active. It's almost like if you set up a website that is actually meant to do something nefarious, you can argue that you came to us.
Yeah, and it's gonna be a very weird next couple of years, I think. Um,
The whole law system has to change, which it never will, but we'll see.
It'll be very interesting, right? And so, yeah, I don't have solutions to these things. I'm not personally studying some of the security components, but I know that it's, like I said, this is a very broad field right now. There's a lot of work in a lot of different places. Probably both for nefarious reasons and for, legitimate reasons, just to make sure to, kind of close out the point, a lot of my work and a lot of the stuff I'm really interested in are the data pieces and the, how to make these things more efficient, because right now they're just not. I joked to some folks today on a call, and I was doing a demo. I think I was using like GPT-4 or something. And I joked to them that, we're kind of back in like the 1980s or 1990s, where we have to start waiting for the computer to do something again. Because we're not used to it. They're like, oh, do you think you can make this faster? And it's like, I can't make this faster. This is actually as fast as it gets right now. And that's why I'm really interested in some of these methodologies, because it's just going to make them better, more capable, and then having them on the edge is going to, in my opinion, be really important.
We're finally back to pushing these machines as far as they can go, and we're back to that sort of point, and that's really exciting for the future of computing. But thanks so much for being on. I would love to keep going, but we do have a time limit. We have to keep.
No worries.
I think you gave us a lot to chew on, I must say. So I do appreciate it. And if they want to find you, and I know you're doing a lot of projects on your own, and I'm sure there's going to be a ton of questions on the ideas you brought forth and some of the things that you've looked at. So if they wanted to find you, how could they?
Easiest would be LinkedIn. I'm not, I'll be honest, I'm not super active on social media. I think when you reached out to me, I think it took me like a couple of days to like get to you, because I had no idea, because I don't check it. I actually got lucky.
You're a real person.
Well, yeah, I got lucky because one of my, we had an intern, and they're like, can I connect with you on LinkedIn? And I was like, yeah, sure. And then I looked, I was like, oh, somebody, like, I've got a bunch of missed alerts, but LinkedIn is probably the best way to get in touch with me.
All right.
And again, I want to emphasize, I am not the master of the universe at this stuff. I'm learning just like everybody else. But it's super exciting, and right now it's really cool because just about anyone can participate. So I hope that folks, get excited and try to participate. Anyone with a laptop nowadays can do this. You don't need a data center, which is great.
Which is great. Thank you so much, Christian. I appreciate it.
Yeah, thank you. It was wonderful. Have a great day.